In this video, we're going to look at doing some stoichiometry calculations. This is a method that we can apply to so many different situations. So if we go piece by piece, we'll start slow, we'll build it up. If you catch on to this method, you are in a great place. So these first problems are called mole to mole. They're the easiest ones. Sometimes you don't even need a calculator. First thing we need is a balanced equation. Stoichiometry is obsessed with ratios in the balanced equation, and eventually we'll use that ratio to compare amounts of different reactants or products. So the first time I read through this statement, I'm going to ignore any numerical values, and I just want to know what reacts with what. So I see how many moles of sulfuric acid would react with 4 moles of aluminum wire. I don't care about the 4 moles, but I see sulfuric acid, and they give me the formula H2SO4 reacting with aluminum. So I get this far, and you can't abandon anything that you've learned previously. We still have to know how to do a single replacement, how to write the products and balance it. So aluminum is normally a +3 ion, +3. Hydrogen is normally +1. Sulfate is -2. So hydrogen and aluminum would like to switch. Now the one thing you don't have to worry about in this entire chapter, no reactions. There will be no reactions here that don't work. They're not going to have you do some kind of calculation and then at the end say, haha, sucker, this thing doesn't even work. So you do not need to worry about checking any kind of reactivity series, solubility charts. I don't even need phase symbols. I just want the ratio in the balanced equation. So I do need to write my products and write my formulas, but you do not need to check any charts or put in phase symbols. So I'm going to bring in aluminum with sulfate. Aluminum is +3. Sulfate is -2. So we'll probably go for +6, -6. Hydrogen gets kicked out, and by himself he is diatomic. Excellent. So we balance. 2 hydrogen, 2 hydrogen. But I need 3 sulfate. And now I need 6 hydrogen and 2 aluminum. Alright, got it. Equation balanced. Now we'll tackle the numerical side, the stoichiometry. So you're always given one quantity somewhere in the statement. 4 moles of aluminum. That's what we start with. 4 moles of aluminum. You must use the unit. You cannot just start with 4. 4 what? Oh, 4 moles. 4 moles of aluminum. And now we're going to set up a proportion. This reminds me of back in the day when we did dimensional analysis and we were switching between like feet and inches or pounds and ounces. It reminds me of doing mole calculations. It's all unit conversion. It's a method where the unit that I have goes on the bottom. I do not need moles of aluminum. What you want goes on top. How many moles of sulfuric acid? Moles of sulfuric acid go up on the top. I want the aluminum to cancel. I already know I have 4 moles. The unit that you want goes on top. Now the numerical values that go in the proportion, the ratio from the balanced equation. The ratio from the balanced equation represents a ratio of particles. But we kind of mentioned that realistically in the lab, you really can't measure like 2 atoms of aluminum and 3 molecules of sulfuric acid. That's crazy. So on a larger scale, we could think of that 2 to 3 ratio as a mole ratio. So I'm going to plug it in. The ratio is 2 aluminum for every 3 sulfuric acid. Bingo, you're done. You just did stoichiometry. And if there's ever anyone out there that's painting some horror story about how terrible stoichiometry is, they're completely off their rocker. That's it. Multiply across and divide on the bottom. 12 divided by 2 is 6. 6 moles of sulfuric acid. Now this makes sense. When the numbers are easy like this, you might not even need to do the math. If this were multiple choice, you could probably pick this answer without setting up a proportion. I have 4 moles of aluminum, and that's double the ratio in the balanced equation. So if I have double the amount of aluminum, I'll need double the amount of sulfuric acid. Instead of 3, I need 6. Wow! This is advanced. This is good stuff. In the same reaction, how many moles of each product would be produced? Now once you have the balanced equation, stoichiometry allows you to compare any substances. We can compare reactants. We can compare reactants to products. That ratio of coefficients is a ratio of moles. A mole of anything is comparable. It's the same amount of particles. So let's say we start with our 4 moles of aluminum again. And this time we'll cancel the aluminum and switch it to each product. So maybe we'll go aluminum sulfate. Let's see here. We plug in the ratio. It's a 1:2 ratio. And I, seriously, enjoy nothing more than canceling my units on a proportion. Moles of aluminum cancel. And whoopsie, I probably should have put this in as moles. Hello, I was just preaching at you. Put all your units in. What did I do? I got too excited. Moles of aluminum sulfate. There we go. All I have to do is divide. This should be 2 moles of aluminum sulfate. SO4, 3. And again, it makes total sense. Every 2 moles of aluminum gives you 1 mole of aluminum sulfate product. You get half as much. So if I start with 4 moles of aluminum, I should get half as much aluminum sulfate. 2. Piece of cake. And then we can do the same thing with our other product, the hydrogen. 4 moles of aluminum. I cancel what I have. I want moles of hydrogen. We plug in the ratio. 3 moles of hydrogen produced for every 2 moles of aluminum. We multiply across and divide on the bottom. Moles of aluminum are out. And what do you know? 6 moles of hydrogen. Gosh, that is not hard. It's the same as the sulfuric acid. It's the same ratio. Again, if I have twice as much aluminum, I'll produce twice as much product. 6 moles of hydrogen instead of 3. This is stoichiometry. It's all about ratios in the balanced equation. So at this point, here's what I would suggest. Try the next one. Get that balanced equation down. Pause the video as you work on it, and then bring it back. Bring it back, we'll walk through it, make sure that you're in a good place. The key to being successful with stoichiometry is practice. You watch a few, you practice a few. If you get them right, excellent, you're in a good place. But if you make any mistakes, then at least you'll see where your mistakes are. You just can't let this snowball and get away from you. You can't think that you can learn stoichiometry overnight. You have to practice in small doses. So pause it, try the next one, and then I hope you get it right. So let's see what we got in 3 and 4 here. How many moles of oxygen are needed to completely react with 4.74 moles of propane? The worst part of this might be getting the formula of propane, right? Prop is the organic prefix for 3 carbons. Ane means they are single bonded. And then we fill up carbon's octet by adding hydrogen. C3H8. That propane is reacting with oxygen, so hopefully you recognize this as a combustion. I don't care about that numerical 4.74 moles of propane. We'll deal with that after we get the equation balanced. So you still need to know all of your types of reactions, how to predict the products, how to balance them. The stoichiometry, that's the calculation part, the quantitative aspect of chemical reactions. So you start with what you're given, 4.74 moles of propane. You set up a proportion to cancel what you have, switch it to what you want. How many moles of oxygen? Oxygen goes on top. If I look at the balanced equation, it's a 1:5 ratio. You need 5 times as many molecules of oxygen as propane. So in this one, you probably need a calculator because your original number is kind of an oddball, 4.74. But if this were multiple choice, you could pick a reasonable answer. It's got to be something between, 20 and 25? You just multiply across. You need 5 times as many oxygen molecules. Multiply by 5. Or in number 4, how many moles of water vapor will be produced in the above reaction? Cancel the unit that you have. The unit that you want goes on top. How many moles of water vapor? It's a 1:4 ratio. For every 1 mole or 1 molecule on a small scale of propane burned, you get 4 times as much water, 4 times as many particles or molecules. And on a larger scale, we use the unit moles. So all you have to do is multiply by 4. For significant figures, you can just leave the same amount as what you were given. So if we were given 3, we'll just leave our final answers as 3 sig figs. There it is, mole to mole stoichiometry. There's absolutely nothing that could make this any more difficult.